give it a few seconds, otherwise. Okay, so meanwhile, I'll just run this off the book. So here what we do is basically we work with something called the pixel, is the basic unit of an image. So all the images are basically multiple of pixels, just like everything in computer is based upon zeros and ones. So pixels are basically, every image is basically a collection of pixels. So we work with pixels in this project. We get a model so that it will identify based upon, it will calculate the pixels for each of the parts, and then it will. Sorry, guys.
It's okay.
Okay, let's go through this. So, not much here. So one interesting thing is we did here, this is Grace, matplotlib.rc image Grace. The one reason for we did this was, of course, that you'll be working with the images converted to grids, and we want to color code that image according to the number in the particular grid. So 0 to 255, with 0 being white and 255 being black. And so depending upon the, sorry. So depending upon the number that we have, the grid would be colored in a shade of blacks. So that's what we did here by matplotlib.rc.
Yeah, by default, I think it uses all the RGB colors, I guess.
Yeah, it's by default it's RGB color. So from, like, again, it's 0 and FFFF, which is combination of 3 to 55, that's black, and like R, B, and G are each 255 each. But here we did grays, which basically will color it according to grays. So we start the project by downloading the data from the Fast.ai library, which has the base path here, so that in the future one we don't have any issues with that. We do a library ls to see what are the data in this mlist sample. Yeah, and we find a few things: clean CSV, item list TST, a bit of models, validation data, and train data. So these are the things we are interesting. One is path valid CSV, and one is path train CSV. So these are directories: path train and path valid. So these are the two directories. So valid has all the validation data that we need, and train has all the train data that we need. Now, as we move into the train directory and try to have a look at what the directory contains, we see that it has two things. One is train 7 and train 3. Right? So it has a directory of 3 and a directory of 7. So we fetch the data from 3, we fetch the data from 7, we sort it, and it's printed here. We take one of the images out of the 3s, and they print it, and it shows a number 3, a small image. It's a very small image. I believe it's 28 by 28 pixels. My system is like, for just for context, it's 1024 by 768 pixels, right? So this is why it's like 28 by 28 is such a small image in the screen that we see here. Yeah. Then what we do is, from this one. Then what we do is we convert. So at the end of the day, all these images contains these pixels, right? This is a number. So what we convert is we do an array IM3. This is a Numpy array function, list array function, I believe. And what we do is we convert it into a list, and we display a part of the list. So 4 to 10, row 4 to row 10, column 4 to column 10. Oh, sorry, column 5 to column 10, and row 5 to row 10 of that image. Yeah. And this is the image that we see here. Now what we do here is, instead of converting it to a tensor, so if you say this is of a d-type unsigned integer, right? So what we do is here, I think it's a Numpy array, right? I don't think it's a list. I haven't seen
the first one is a Numpy array. The second,
right?
Yeah.
I didn't do this step actually, but I like it. Shouldn't they have prefixed it with np? Otherwise, I don't think. Or they just rolled out all the methods. Don't know. Or maybe yeah, they. I mean, fast I exported this method. Yeah.
Maybe they did. Let me check.
Yeah.
Yeah,
Just
actually,
do, just do a who
they
and it will tell you.
yeah, actually they do import all the necessary packages from NumPy,
I
Torch.
don't
So,
recommend this doing this because it confuses
yeah,
which my library this method belongs to.
yeah. Actually, I was also confused a bit in the start, but then I went and saw the source code of the fast day. So that's
Mm,
when they were directly doing from Torch import tensor like that. So
yeah,
Yeah, I think they did from NumPy import array somewhere. Yeah.
right.
That's why you have it like this.
I can't execute this, right?
No, you cannot
Yeah, I
execute
can't.
on GitHub, but yeah, you could
Yeah.
probably do it on a local machine if you want to. So I'm doing all of this stuff on my local machine, which doesn't really have a GPU because, I mean,
Yeah, no, but
not,
like it doesn't require till a certain point here.
yeah,
But I think down the line it will be very helpful if you have a
yes,
CUDA. Okay, so moving on here, there's an array that we have here, and what we did again was we took the same image, we can the same portion of the image, row 5 to 10 and column 5 to 10, and we move to a tensor, right? That's a PyTorch tensor, and that we what we saw here, see here is d type is equal to torch dot unsigned integer 8. So what we are creating is right now a torch tensor, which functions most very similar to a normal array, sorry, a NumPy array, but with the difference that there are a lot of additional benefits. But one very key additional benefit is that it allows you to work with GPU. So NumPy arrays, you work on CPU, work on GPU, it doesn't matter array. But Tensor has this capability. PyTorch has built it with which it can work. It can work in GPUs very fast. Like it can multiple batches of tensors can work very fast. Okay,
right.
so yeah, we do this, and what we do this is you see this is basically converting into data frame. So what we see here, this data, right? It's a bigger data portion of that image, and we see in a data frame table, and you see this is basically like the tree here that
Yeah,
for this portion of the tree.
yeah. If you run
You
it in the
see
NumPy
this
in a Jupyter notebook, then gradients it. Oh, you already have it.
color grays if you said, yeah. This is basically what is much to actual black, which is much closer to 255. If it's 0, it stays white. If it's 30, it's much more whiter than blacker. 187 is somewhere around the middle. So it is a little darker shade of gray rather than lighter shade of gray.
Right.
So that's what we do here basically. This was a very important thing. I think we should always do this, stop and think, just we shouldn't just read on this. Basically say that when we want to try something, let's try before we see the solution of it in the book. Okay, what happened to it? Okay, so
Yeah.
the first approach that they try is basically the pixel similarity.
Did
Um,
you guys think of anything else apart from what he has shared, like pixel similarity, getting the average of all the pixels?
so actually, I had. I mean, I wouldn't have done. I hadn't seen this, and that's why it has stuck with me.
Yeah.
Um, so it was similar to pixel similarity, but instead of taking the mean distances, I just took an absolute distance, uh, which did not. I mean, it didn't work well. I had this like just so basically uh, take an average and then take the absolute of how what the difference is, and yeah, I had that thing in mind.
Could you repeat that?
So so basically kind of what, so basically this all we have, I didn't know how to do it, like they have done the stack
Right.
and all, but like what I had thought of was take a for loop, go through each image and then add up all the threes that are there, right? Take all the threes and add it up. So you will get a rough calculation of this. So basically, I would have taken an average out of it, right? Yeah. For example, this is like of every threes, this will be some pixel. For example, 4 would somewhere around, average would be around somewhere around 120 or 130, right? And then I would have calculated the absolute value of the difference between one image and the other image. But I didn't know how to proceed after that, like how to correct the data and stuff like that. That's what I had thought of doing. Like just calculate the difference between the a test image and the average image.
Okay.
But like, how to proceed after that, I didn't know how to.
That kind of seems would have been similar to what he did, right? No.
Yeah.
What I thought was,
think.
Yeah.
Sorry.
Go ahead.
No, go ahead.
So what I thought was, I would, if there was a new image, I would take every pixel's distance from all of these, training images that we have. So, and then average them. That adds another for loop, I guess, like 1.
Yeah. I think it's the same. I think the same thing in a different way.
Yeah. Yeah. Always the same thing. Right. I guess we can.
I think we got it. Oh no, it's still another.
Even I was facing issue yesterday when I was running on Google Cloud. I couldn't find resources in our region, East Asia. That's why I had to do it on my local machine eventually.
Okay. So we saw here. Okay, fair enough. And then what? So it's pixel similarity is about basically. Okay, we'll go through it. So what they did first was, instead of having an array, like we saw here, right? That they converted the tensor. They converted each to a tensor. So a tensor of image 3. And what's this image 3? It's basically opening an image, right? When you do an image with open, so that's what you are able to read that image, or you make sense of what that image, how it should be structured and all. So for each of the image in 3s and 7s, they convert it to an array of tensors rather than having it. Yeah, and we see that there are 61317s and 61313s and 6265 in our training data set.
Right.
Yeah. Do we have to? I think everybody knows about list comprehensions, right? List comprehensions.
Yeah.
It's a Pythonic way of doing list. Pythonic way of doing a for loop.
Yeah. And saving the results of this.
Plus, it's telling in statistics, a comprehension is when you declare a set. Okay, so we just converted this tensors of arrays of tensors, right? 7 tensors and 3 tensors, and just to be sure, we just took one of the images out of this, and we see that this is the image that is printed. Yeah.
Yeah. Why does it show in white and black instead of black and white like before? Probably they changed. So
Which one?
Here. So the number is in black.
Oh. I think this is what it is. I think so. This is how it is. Like this is black on white is basically how it should be. So this is the one. But I think this is the image API that they use, right? I think that's the one to do here. So image API. Maybe that takes a black as a default, or maybe because it's a white background, it takes a black as a default so that data can be shown.
Yeah. Yeah, and show image is from Matplotlib. Those are two different ways of displaying an image in Jupyter Notebook. The show image method comes from Matplotlib, and the other one we are using it from the image package.
I think that makes more sense. Yeah. So thanks, Ashwin. And yeah, so image with source that image, and so what we do here is basically something to do as a stack, right? And And so something that we do here is stack. So what does stack do? Excuse me. So what does stack do is, so basically we have an array of so if you see here, we have an array of images of 6131 images, right? We don't just have that 6131 tensor, right? So what stack does, it converts it into a 3D. So this is basically a 1D right of now, like 1D array as of now. It converts it to a 3D array, three-dimensional array of size 6131 and then 28 by 28. And we convert it to a float so that we can divide it, and we divide it so that we can normalize it. So we, rather than having to work with numbers between 0 to 255, so I think it's a lot more mathematically easier and computationally effective to be working within a range of 0 to 1. So that's why I think we did a division by 255. I think that's it's my assumption here that we'll divide it by 255 because that would be mathematically efficient. What do you guys think about it?
Yeah, it's like scaling the value.
Yeah,
That's the reason why we do it. It's mathematically more efficient operating on 0 to 1 values rather than different ranges.
okay. So stack is basically converting it to something called as a rank 3 tensor, right? So this is basically a tensor of rank 1, right? If you just do tensor, right? Tensor like this way, this is a, so if you do a tensor of a scalar like number 1, then it's a rank 1 tensor. If you have a 2D array, you convert a 2D array to tensor, that's a rank 2. And this, what we see now, is a something called as a rank 3 tensor.
Rank 3, yeah.
Okay, and we can actually see the shape of it by this. This is a 3, so this is a rank 3 tensor, and which is similar to what a dimension is. So because it is a 3 rank 3 vector, basically means it has 3 dimensions. To put it on a number scale, it would be like x, y, and z, a rank 3 tensor. You could always do also an ndim to get the dimensions rather than doing length of stack trace dot shape. You could also do the ndim, use the ndim method to get the dimension of the spread. Now here's so we got this mean images, right? Sorry.
Right.
So we got this tensor, like it's like a combination of 6131 threes, right? It's a combination of 6131 threes and a combination of 6131 sevens, right? And what we then do is we take a mean of the stack, and so basically we all add up the 6131 data and then take an average, and then so this is what the average tree image looks like. So when you do this, it looks like an average tree image. I would have done it a bit like I had taken the same pixels 4 to 10 of this so that we could see much more clearer what the numbers, because it appears a bit hazy here. But yeah. Okay, so this is a number 3, and similarly this is a number 7. What basically they did here was they took a random image of A3, okay, and they did so okay. Before we go ahead, like there are two concepts that we need to talk about. One is the L1 norm and one is the L2 norm, right? So L1 norm is basically the difference, the absolute difference, like A minus B, but the absolute of it. The absolute of it means that it's a positive number. Even if the value is actually negative, you convert it to a positive number. So that's the L1 norm. And the L2 norm is basically the square of the differences. For example, A minus B, but square it. So again, it's a positive number. Square of the differences, and then you take the square root. So which basically almost makes it like the it's a different value, but it'll always be a positive value. So this is done so that we have an absolute difference. We don't get in the concept of negatives and positives, because if you add every negative and every positive, then you would get a 0, which would be counterintuitive.
Yeah,
And
right.
why we do this distance is basically to calculate what is the distance of the whole image. So how distant it is from the mean, right?
How they are. Yeah.
So this is the mean. We have a mean, and we take an average. And what we want to know actually is how distant, how far apart from the mean image is a sample image of ours. So that's what we have two ways to calculate that. One is the L1 norm, which is the absolute difference, and one is the L2 norm, which is the square root of root mean squared error. Actually, I think root mean. Yeah, right. Sorry. There is another concept called as mean squared error, which is basically not taking the square root. So what it does is basically it amplifies the loss it amplifies the distance. But we'll go through it a bit later.
No, if
But
you do not take the square root, even then it would still be the same. I mean, the impact of the loss function, I think, would still be the same.
agree, but I think we'll study later about gradients and stuff like that. So, for example, there's a difference. You are two-part difference, right? Shall I explain? Shall I explain my understanding now, or shall we do that later?
Yes, you can.
So, what I think is, for example, if we have like a distance of 2, right? The absolute difference is 2, and we square it. Now it's 4. The difference is that you learn much faster. You reach the local minima or the function very faster if you have a different, if the value is squared. Like, think about this. The value is 2, right? So you will take a slow step. Okay, I have 2 steps to go, right? So you will take 2 steps. But if you have the value as 4, you will take a bigger step so that you can reach it faster, right? So that was one of the concepts that really when we talk about gradients and stuff like that. So yeah.
So when
But
the loss function is squared,
uh-huh.
then it would go towards it would move faster compared to when you do a square root and then use it for the gradients.
Yeah. So basically, the intuition is that the loss would be much more if it's a square
Or
basis, right?
for larger errors, it would be higher.
So it would be for example, it amplifies. You have 2 steps to go, then it will no, you have 4 steps to go, and then it will say, okay, I have to reach faster, and so that the gradient will be a bit more better.
Right. Okay.
Okay. So yeah. So basically, these are two functions. One is the absolute mean or the L1 norm, and one other was the root mean squared error that we are talking about right now, which is the L2 norm. Okay. And it goes about till that these are the two functions that are already present: F1, I1, L1 loss, and then the MSE loss. Right.
Right.
So yeah, it mentioned the difference between L1 norm and the mean squared error is that the latter will penalize bigger mistakes more heavily than the former, and be more lenient with small mistakes as well. So that's the difference. It will, like, it gets amplified. Like 2 square is 4, so it will just amplify it more. Now it talks a bit about the Numpy arrays and the PyTorch tensors. So it says as similar like PyTorch is basically similar to Numpy with the addition of using the support of GPUs to calculate gradients and to make multiple computations at once. And one interesting thing that I learned here is that Numpy has the facility of a jagged array, whereas PyTorch doesn't have that facility. So, like here is what I mean by a jagged array. So, for example, in Numpy, you can have something like this: 1, 2, 3, 4, 5, 6, 7, 8. Yeah. This is something called as a jagged array, where you jagged array over basically where you have, so this is a one dimensional of 3, this is of 2 and this is 3. I think NumPy array has this facility where you can have this jagged array. Arrays potentially being of different sizes. But in case of PyTorch, that facility is not available. It has to be, I mean, there is no facility of jagged array. Yeah, it has to be all of the same length and height.
This facility is there in TensorFlow. It's
As
called
in?
as
Okay.
yeah, it's in TensorFlow. It's called as a ragged tensor in TensorFlow.
Okay. So
So
not the
it's
normal
okay.
tensor, but there's a
Yeah, ragged tensor.
okay.
So if you ever want it, then you can use it from TensorFlow framework.
But it exists, like it's not that it's not there. And this rag tensor is the default of Python, like they provide this.
I think so. I'm
Or
not
isn't
sure. It's not a default one, I guess. I think you need to define a ragged tensor when you have a different sizes in your tensor.
okay.
When would you like to use something like this?
In sentence encoding, maybe.
Okay, I'm not really sure about that.
Suppose you have 3 number of sentences with of lengths different sizes, right?
Mm-hmm.
But you need to stack them together in a tensor after
Okay.
encoding them. So they will have different sizes. So PyTorch tensor doesn't allow it, but a ragged tensor in TensorFlow allows that.
All right.
So TensorFlow allows it, right?
Yes, yeah. I'm not sure they also have in PyTorch, but in TensorFlow they have it.
I mean, here it's mentioned. I haven't done a research more on this jagged array stuff, but here it's mentioned a PyTorch tensor cannot be jagged. It always requires a shaped multidimensional rectangular structure. That was my basis for saying that. Okay.
Okay.
Okay. Okay. Moving on. So here are basically a bunch of examples regarding tensors. What are the operations you can do with tensors? So it's a normal. Basically, data is a normal Python list, 2-dimensional list, and here we convert it into NumPy array, and here we convert it to the Python torch, and we see that it looks same. You can do the same operations if you want to the first row, first column, and multiples of, like, there's a specific first row, these many columns. You can do the same, and if you even if you do a +1, so this is behaves mostly like a NumPy array, yeah, using all the examples that we have here. So which makes it easy for us to get on board with it.
Tensors.
Yeah, to get on board with
Yeah.
the tensors. And now comes a very interesting topic of broadcasting.
Mm-hmm.
Yeah. So let's go through it and then we'll see it. So here what we do is basically valid 3 tenses. We do a talk. So this is what for the training set what we have done. Just did it for valid set. We for each of the image in valid 3 or valid 7, we converted it to a tensor and then we stacked it so that we now have a validation size of 1010 and of validation 3 size of 1010 and validation 7 size of 1028. And then we get to calculate the distance. So we had talked about the distance, right? The distance between the mean and the sample image to check how far you are, right? So what we do here is basically we pass an image of 28 by 28 and another image of 28 by 28, and we see that a minus b, so it calculates the difference and then do an absolute and then takes a mean to tell you how far it is. So basically an average of all the pixels. So some pixel will be, for example, 0.5 apart, some pixel will be 0 apart, and stuff like that. So on average, you have a distance of 0.1114, right? So this is the mean of the average image index.
Right.
Now here is where the things get interesting. With PyTorch, you don't have to. They don't have to be both of the same sizes, right? So this is a 28 by 28. This is a 28 by 28. And when I mean both should be of not of same size, it doesn't mean that this can be 28 by 28 and this can be 40 by 40, right? But what we can do is we can have this concept of broadcasting is introduced here, wherein if you have a larger copy, for example, if this image is of multiple 28 by 28s, then the other one resizes, right? It resizes to be like that. So
Yeah. So basically, if it has an additional dimension apart from the,
yeah, right. I think that's a
then
perfect word.
you
Additional
drop,
dimension. Yeah.
to that many.
Yeah. So the other one, which is of the lesser dimension, it adapts itself to be of that particular size as of the other one.
Right.
So that what we did is, so that what we did with that was basically we can use that concept to call the mness distance for all of the valid data tensors. Sorry, for all of the training data tensors to see what is the distance of each of it from there.
Mm-hmm.
Yeah. So that's what I think would be doing there. So yeah, we did what we did for is basically instead of passing one image, we passed multiple images. So this is a tensor, I believe, of around approximately 1008 by 28 by 28. So
Yeah.
three-dimensional rank 3, and this is a rank 2 tensor. And we got basically a rank. We basically got a rank 2 tensor of
Rank
the
1.
images. It's a rank 2, right? Rank
Rank
1.
1.
Yeah, it's a
Yeah.
rank 1. Yeah, because this is rank. Yeah, it's a rank 1 of all the pixels that we get here.
Yeah, it would have been rank. So if it's just one value, do you call it a rank 0?
No, still rank 1.
Still rank 1.
Okay. An array is
That's,
also a rank 1. I mean, one-dimensional array or just one value, both of them are rank 1. So,
yeah, it's a rank
Actually,
1 tensor.
it would
It's a
not be
vector,
a
right?
vector then. It's a scalar.
Yeah, the first one. Well, it's a rank 1 tensor in both scenarios.
okay.
Yes.
Okay. We did a shape calculation of it, and we got that this is 1010 difference. So we basically got a mean distance calculation of each of them, right? So for each of the images that we have in our validation set, we got a mean distance of mean L1 distance from the mean image.
All right. Do you guys know how how it would, decide on which dimension it needs to broadcast? What if the, shape of the smaller dimension tensor was 1010 by 28? So would it multiply it by 28 or would it not do anything at all? Or would it get confused about it?
That's an interesting one. I think we have to try that one. I mean, I didn't
Yeah.
try it.
Okay. I haven't tried it either. I just came up with the question as you were talking about.
Okay, my system is auto-controlling itself. What's happening? I'm sharing my system, right?
Yeah, you're sharing your system.
Okay, what is happening? Okay, hold on. I think I got the issue. Just give me a minute, yeah?
I think think it was a wireless mouse or something that someone
Yeah,
used.
it was a wireless mouse.
Happens with me all the time.
Okay. Okay. Sorry. So why did it do it? Opened up the console. Yeah, we did this broadcasting. Okay. Yeah, and we try to get an accuracy. Okay, we defined a loss function, I believe. Did we do that? No, we
I
didn't
think
do
that
it.
we are using just the accuracy.
Yeah. So basically, yeah. So after we defined two functions. This is like a loss function here. So basically, okay, sorry, no, we didn't. So basically, here we are telling whether if which is the smaller of the distance. For example, is that image small? The distance, the mean distance, is it nearer to 3 or is it nearer to 7? Right?
Yes.
If it is nearer to 3, it means that this is more of a 3 than a 7. If it's nearer to 7, we see that it's a nearer. We will predict that it's a 7. That's how we calculate, and that's what our accuracy function is. So how many accuracies that we have, we get it. So basically, is 3 here is the function, and so we check the accuracy of 3s by saying how many. So for each of them, what was the accuracy for it, and we get approximately 91% accuracy with the 3s, and we get 95% with the 7s, right?
98% with the sevens and
98,
5% in total.
average of 95%, which is, I guess, pretty good with it.
Yeah.
So we were classifying two images, 3s and 7s, and what we did was we were able to do it very simplistically without the use of GPU and all. Now we come to the concept of stochastic gradient descent. I actually have to look up. I had this. Sorry, what this particular word means.
It basically means you're taking in batches. Stochastic means taking in batches. That's all.
Yeah. Okay, so it means random. Okay, random gradient.
Randomly taking batches.
I think Jeremy defined that, right? He said that. So, what's the difference between a gradient descent and a stochastic gradient descent? And he said that the difference was that we do it in mini batches. We do it as, that's why we tell it as stochastic gradient descent.
Yes, mini batches. Yeah.
Okay, so so gradient descent is basically consists of these 7 steps. What we talk about. Basically, you initial. So basically, you so suppose you are on a hill, right? And what we do with this loss definitions, what this is MNIST loss function that we did was basically calculate the mean square error and stuff like that, right? So what it both means is that suppose you are on a hill and your destination, suppose you start somewhere randomly on a hill, right? And your destination is that you have to reach the minimum point of that hill, right? So that is what as in function we call as a local minima. So what this tells is that we have to find out a way so that we take our steps towards the local minima, right? Do you guys follow what I'm trying to say?
Yeah.
Yep.
Okay. So that is what so in mathematics, you basically a max or a min is like we can define by um, calculus. Like how this is basically your min is where you are the lower point. Like where is the max, the min is basically where the gradient is quite literally 0 approximately. So we want to go towards that local minimum of this function. So if you have a slope, if it goes up, then we should go back. If it's a slope that goes down, then we should be going forward, right? So if you are on a slope, So that's what we are trying to do with this gradient. So that I'm trying to give an intuition of it. So suppose you are somewhere on a point on a hill. Your what you want is basically to reach the max, to reach the local minimum of it. So you want to take step to reach that one. So how do we do that, right? Basically, where you are standing, you just take a distance, you take a slope of like you go back and you go for top and you go forward 2 steps and just calculate which is giving you a negative slope, like which is the point by which direction you will be able to go down, right?
Yeah,
If
basically
you
going opposite to the direction of the slope.
yeah, so that's what you want to do, and then you that is called as the gradient, because gradient is a slope, and descent is basically you want to go down, so we have to figure that out mathematically, and that is what gradient descent is. You try to go down the gradient. Yeah. So for each, and like we have to do that for each of the pixels that we have, and that's why we initialize a weight for each of the pixels, and we define we define a predicting function which basically predict with those set of parameters what is your predictor, with those set of weights of parameters and the input that you have, what's the output going to look like, and then based on this predictions we'll calculate the loss. So what is the loss? It's basically the difference between your predictions and the actual output, right? So you tell, okay, I am so far from the actual output, or I'm very near to this actual output, and based upon this predictions we calculate the gradient. So how far do I have to go, how big a step do I have to take, is it am I too far, am I too less? So depending upon the function that you have, the gradient will be calculated accordingly, and then based upon that step we adjust our weights a little bit, and there is a bit of learning rate also that comes into picture here, but at the end of the day, like it does is basically to adjust your weighting parameters so that you are much more closer to the actual model, and then we repeat this process. So basically we again predict, we again calculate the loss function, we again do a gradient, and again we do this repeat process. We'll do repeat this process until our prediction meets our target. In this case, our accuracy or our error rate, whatever we say, until we meet that parameter, we should be iterating. And this is what basically it looks like in an image. You initialize the parameters, you predict with your set of parameters and input, you calculate the loss, you take the gradient, and you adjust your weights as it if it's what you want, fine, otherwise repeat.
Okay. Should we try to implement this in a live coding session? I mean, just an idea.
Should we what?
Should we try to implement this in a live session? I mean, like right now.
Yeah, I actually had thought of doing it, but let's see if it's just that. Or if you want, if any of you guys want to do it, like I'm so sorry, you are free to. Like I don't have a machine right now, and my local machine will take up some time to set up. Or shall we do it in a notepad?
I could share my screen and then we could try.
That would be great.
I haven't implemented it myself, so don't expect me to. I just went through the video. I didn't implement it, so
yeah, that seems fine. Yeah.
Also about stochastic gradient descent. So when you are doing it in batches, then it's called the mini batch gradient descent. And when you're doing stochastic gradient descent, that means that you're taking one sample at a time to train the gradient.
Okay.
This one. All right. So I just watched the video. I haven't done it, so it might seem like we have the steps here. I'll just copy this type so that you can follow along the same thing. You guys can see my screen, right?
Yep. Okay.
Yeah.
All right. So how do we go about it? Let's call it weights.
Mm-hmm.
That would be tensors or
Do you have some data?
no.
Need to import the data, right?
Yeah, I'll use the data
Okay.
that he will use this function that he has here. This one. All right, this becomes our data set. How do we initialize the weights? Tensors, is it?
Mm-hmm.
Tensor dot?
Tensors. Array function, just
Isn't it something like this? Arrange 1 to 3. No. Torch. This might actually end up taking a lot of time. Do you want to control my screen and then do it? If you're already familiar with it. Can you hear me? Hello?
Yeah, I can hear you.
So does either of you want to
hey,
control
sorry.
my...
Yeah, Harshant, if you want to take control. It's a torch, by the way.
Yeah,
Even I
I
didn't.
changed it to torch. I can assign you control and one of you could do it. Sham, I'm assigning it to you.
Yep.
So you should be able to control my screen now.
Okay. Okay. Can I? Am I doing this?
Yeah, you're doing it. The steps are before the cell above. So we initialize the weights. Then for each image, use these weights to predict whether it appears to be 3.
It's taking a bit types. Like I type something like it takes a bit time. I think this is a bad idea.
Yeah, maybe this.
It takes quite a while to show up.
Okay. So I'll cancel the remote control then.
I can't use the dot somehow. You know, I can't click the dot.
All right, let's do it some other time then.
Yeah,
Yeah, I'll stop sharing. You can share it.
I'll try mine. Okay. Can you guys see my screen?
Yeah.
Yep.
It's a bad day. And this is the first time it's happened to me that paper space is saying error.
Okay.
Every time, I never had an issue with even getting a machine.
Right.
Okay, so we take an tensor array, 1D array, one-dimensional tensor, right? We initialize this to a float of 0 to 19, like a 20 bit array. And then what basically we do it, we assign it weight. So this is okay. This is a function with related to your time. Yeah. So basically, this is a constant again plus again a constant into time minus, so ax square plus b, kind of, that's what it is. I'm
Right.
not sure why they did. So this they would have. So this is 1 plus torch random 20 into 3 is a constant, and then this is a function of x square. So where your function
First
of
one,
time square.
the first one
Pardon?
is the error element that
It's
they
an
introduced.
array. Yeah, it's an array.
No error. I mean, that's the, you know, noise that they are introducing for each value for each time.
But even this is the numeric one is also a bias. Right? Both of these are bias. Right? This is also a bias, and the number one is also a bias.
Number one.
Plus one.
I'm not really sure. That is something that is the constant. So ax squared plus bx plus c. So c is 1, all right? And, you know, a, b, c are the parameters that we find, and torch dot randomness is the noise that our function wouldn't be able to capture, because it's different for each row, each time. Rest of it is a
Yeah.
function of time, but the
But
first
okay.
element is not a function of time.
Yeah, but like yeah, you're right on this, but I was saying this speed is like this parameters are initialized one time, right? So when this function is basically, when you calculate this f speed of x, these are all at the end of the constants only. I understand it's a noise that we are randomly inserting to the function, but at the
Yeah.
end of the day, they are all constants, right?
Yes. Yeah.
Mhm. Yeah. So basically, they are okay. I thought them of constants, but they are a noise that we're introducing so that each of time our experiments are in the same. Like there
Yes.
can be a bit of difference to each of our experiments.
Yeah. It
Okay.
doesn't follow an exact quadratic.
Cool. I hadn't thought about that. Okay. We have just an x square here. I don't think we have a bx, just ax
No,
square
we
plus
do
c
not have.
with a random. And yeah, we have this parameters function, basically f of time, and parameters what you pass it. You That's the function f of x. And then we also define our MSE, the mean squared error, basically predicts spreads into targets square mean. We are not taking the square root, it's just a spreads into target square dot mean.
Yeah.
And we do this, which brings up the concept of requires square. So params is equal to torch dot, we take three parameters, three randomness,
Right.
right? And we do this requires grad, and especially important is the small, which is make it inline, right?
Yeah. In place.
Yeah, which is a bit weird to me. Uh, I'll tell you why it's a bit weird to me. I mean, I'm not saying it's not perfectly fine or not, but
Mhm.
when you basically, okay, in different other programming languages, like I have worked with Java, JavaScript, and stuff like that. When you uh, do this one, right? So when you are doing something in place, you don't return it. You don't return the same object
Yeah.
because
Right.
it doesn't make sense, right? You don't return a value. So I would have understood this if this was params is equal to torch dot random 3, and then the next line it does params dot required vat finish. So the concept is when you're returning, it basically means that your original array is intact and you are creating a new array, and that's what you're passing it.
I think, yeah, even I was confused about that. But
Yeah.
when you are saying requires grad, I don't think it only tells that these parameters are supposed to calculate gradients in place. So this whole thing can be considered class maybe, or a method, a class probably. So whenever you do any exercise on these params, it calculates, it saves the operation so that later on if you do a backward, then it can calculate the gradients in place. So when you do backward, right, it doesn't return anything, but it saves the gradients.
Yeah. No, what I meant was basically you should be able to do this as well. Like I have not tried it, but I think this should work, right? If you do requires dot grad, this should work. You should not have to return again. You have to not reassign that. If this is works, I'm totally fine. We generally don't see it in other programming languages. We do have to return something and assign it to it. When I mean it's in place, it is modifying the parameters, this object internally. I mean, that it returns is not an issue, but what I'm more interested in, it modifies this params object, right? And it doesn't return a new one. So that is what was more interesting. Because in this example, we did a RAND3, but in normal applications, we'll have the data and we'll want to modify that data. I should. So, I mean, if this works fine, that's all I care about. Whether it returns something or not is generally a feature. Like if you're returning something, it generally means that you are not modified the original data, right? So that was the assumption. But like if this works, I'm fine with. I haven't tried it actually. I got this later thinking about it. But I
I'm
hope
not
this works.
sure whether this works, but if you're uncomfortable doing this, you can just do torch.rand of 3 comma requires grad equal to true.
Yeah. Okay.
Yeah, even I find it uncomfortable doing this, so I will just do 3 comma requires grad equal true.
And there was something with related to branch also. I had that in mind. For example, it says that keep your original branch same or something like that. Not here though. Let's see later. Yeah. So this is the original weighted parameters that we got, and we just to see it, we just have this cloned here. Okay. Now what we do is basically we do a preds. We predict the that for this parameters, what is the output for the time function. Like this is the pred, and then we do a scatter plot. So for each of the x's, the time that we, so this is the time array, and this is the preds array, preds output, and this is the actual function. Like this blue is the actual function for the time, and this is the output that we predicted, which is vastly different from what we wanted. Yeah. So then we have this loss function that we define. We calculate the loss, and we see that this is a tensor, a rank 1 tensor, a scalar actually, which has a grad function, basically the function that we want to apply, which is the mean backward 0. Now I think I have seen different kinds of backwards. I've not noted it down, but there are different types of backwards. It's not always mean backward, but there are different. I think it's mean, yeah, because our f is basically calculates the mean. I think that's why this is a mean. This function is a mean.
Yes. When you do a required grad, it will basically remember all the computations that you did on those parameters. Since you are doing mean here, it's remembering that when I do a dot backward, should remember that this mean has been computed on those parameters. So it has to look through all the chain that has happened before. So that's why it's mean backward here. But when you do dot sum, if you're doing dot sum in the f function, then it will be a sum backward of 0.
Okay. Okay. And how does it use that information? Do you have any idea about that? Like, does it perform differently when we use any of that? Like, as if it's a mean backward, it's a sum backward. Is it different?
Yes, yes. I
Okay.
think it performs differently because you will basically be taking mean of those gradients if you are doing a mean operation before. Like if you have mean backward, right? You will take a mean of the gradients, and if you have sum backward, I think it will take some of those gradients. Even I'm not sure how that dot backward function. I even tried to look at source code, but I couldn't understand much regarding that.
But from what I understood, see, yt is equal to f of xt, and it will do accordingly. For example, if it's an x square, it will say 2x, right? Whatever is x. So would it really matter what the backward was? what are the parameters that we use, for example, whether we did a mean or whether it's some, because a
I
gradient calculation is a function, right? It's basically a derivative function. So d of f of x
yeah,
by d of x. So for that we don't, I'm not sure like how it was. Yeah.
yeah. Even I had to look more into that.
This is why these groups are important. You think about some stuff that you never have thought of. Sorry. Yeah. Okay. So basically, we did this. We calculated the mean. We did this lost or backward, which is not like, there is nothing called as forward, right? It's basically back propagation that happens. So to recalculate the weights according to the steps. Now I had seen an image where like if it rolls down the graph, and if when it does backward, it basically does an unrolling of the graph that PyTorch creates to when you use this backgrad to calculate the parameters, gradient parameters. So when we do this, and when we see this params dot gradients, basically we'll see what are the gradients for that, what are the parameters value after we do that as of now. And then when we multiply it with a learning rate, it will modify the data by gradient into this much. So our original parameters, do we have the original parameters? Have we printed it? We have it, right?
He's not printing it anywhere, but he saved it in original params.
Yeah. Okay. So this is basically the gradients that are calculated after we did the function. And then we, to modify our parameters data, we have to change it by this much. Basically, this statement is that you have to change it by this much gradient along with the learning rate. So this is what we call as the learning rate. So learning rate, I think he had given a very good example about this here. Basically, learning rate is the how big a step you take so that you reach your function minimum.
Mm-hmm.
Yeah.
Right.
Yeah, and so this basically we did a params.grade into which auto calculates the gradient parameter, and we see that the params has now changed to this data. Excuse me. So okay, so this is what basically we see. We do a learning rate, and then you update the data, and then we do basically a none function so that our gradient isn't saved anymore. Yeah. Yeah.
Why do they clear the gradient after updating it?
Because when you do dot backward, it already calculates the gradients, right? And again, when you do a dot backward, it will take second order derivative, but we need only the first order derivative. That's why we need to reset those gradients again, because it remembers all the computations that are being done before calling dot backward function.
Okay. But why would it calculate the second order derivative if backward again? I mean, it should calculate the gradient of the change that happened, right? Not of
So dot backward will calculate the gradient, right?
of the change that happened when we moved from a certain step to another.
So if you take x square, the first dot backward will calculate 2x, right?
Yeah.
So it will remember we have already calculated gradient and we have 2x. So when we again call dot backward, what will happen is it will
Convert into 2.
Yeah, yes. It will do a derivative on the 2x, not
Okay.
the x square. So that's why we need to reset those gradients.
Okay. All right.
Hey, thanks, Yashwant, for the explanation.
Yeah, no problem.
Um, yeah. So we adjust our data accordingly, and we set the gradient to none. Yeah, and we predict it, and we see that when we do a we do a graph with the newer parameter into predictions, predictions, which takes the new parameters, then there is a slight improvement, right? So, and if we do it multiple times, we see that it has improved a lot from where we had initially. So the weights have basically improved a lot, not still as good as like we wanted to, but has in around 5 or 6 steps. I mean, it was 10 steps. It has increased quite a lot. So that is what basically gradient descent is all about. And we apply this function. We apply this concept of gradient descent. We can apply to this MNIST loss function. So we concatenate the train X model into the stack 3s and stack 7s into one train X, and similarly we do it with train Y. And because this is basically a row 1 vector, we unsqueeze it to convert it to a 2-dimensional torch, right? And yeah, sorry, we do have view 1 here, so that we do. So if we don't know like how to what length we have to do it, we have. So we do this view -1, which means that as long as it happens, I'm fine with it. Which I want 28 by 28. So this is what this view does. So it groups the data 28 by 28 that we have as the second and the third, and then -1 says that as long as can go. So because we don't know the size, right? What we could have done is we could have taken length of stack 3s and length of stack 7s, and we could have added plus instead of this. But instead of this, we can just do -1, which is I think it's better.
Yeah, it's handy.
Yep.
Because PyTorch will. Yeah.
You don't have to
Yes.
calculate it.
Yeah,
PyTorch will do that for you.
Yes.
So that's a small thing that's taken care of by PyTorch. And then we convert this into a data set. So what is a data set? Is basically a zip of each. So each of the elements will have the X and the corresponding Y. So when we do a zip, basically it will have that X data and that Y data. So we have 1, 2, 3, 9, 6, right? This is the Y shape. Sorry, this is the X shape. This is the Y shape, right? So we have the similar amounts of like similar rows of X and Y. So each row will have its version in the zip one, and this is a list for the 120. So there will be 1, 2, 3, 9, 6 items, and train X will be 784. Train Y will be 1. So that's the kind of shape we are bringing, so that we have a collection. We have one X and Y. We don't have to do two, like don't have to have two data sets, 2 data points. We just have one data point, and we can unravel the X and Y from that. Right? We do the similar thing for valid data set as well. And here is something we do. We do the init params. We define a common function for init params, which basically says create a random torch of random size, right? Create a random torch, create a random size tensor with a standard deviation of 1.0 by default, unless you supply a first. And we apply, so this parameters is what will be calculating the gradients upon. We'll be applying the gradients to this parameters. And we do this init params. And this is where I was stuck for a long time. I had forgotten to, I had just passed in 28 by 28/1, which meant actually that I wanted a 28 by 28 size with a standard deviation of 1. I had forgotten the second parenthesis. And this led to major things. I mean, it didn't break anything, but like output wasn't expected. What like the output wasn't what I expected. But yeah, it happened like that.
Can
I
you
mean, okay. I mean, it's not easily explainable. I would request you to try this out. Right, this is 28 spot. This is 784/1, right? This basically,
Yeah.
this is the size that you are saying. Give
Yes.
me
Yes. Yes.
a init param size of 784/1. Right? You are
Mm-hmm.
saying this. What I had done was I had forgotten this second set of parentheses. I had just given the outside parenthesis. So
Okay.
basically, I was initializing a parameter of size 784 with a standard deviation of 1.
Yeah.
Mm. Yeah. Got it.
And it
Yeah.
didn't break anything, but it didn't do anything. Like I trained my model multiple times, and it did not do it. Like there was no betterment. Like the models were basically the gradients were not calculated. They were
Mm.
the data was not changed. So if I did a init param now, and after 10 iterations of everything, I did an init param, it was still the weights of both were still the same. I still
Mm.
don't figure out why that happened. I'm still working on it. But
I
yeah,
think
it's,
you need to give a rank to tensor
yeah,
instead of rank 1, because if you
yeah.
don't put those parameters, it will take a rank 1 tensor.
And it'll create a rank one tensor.
Yeah.
Yeah, that's like, yeah.
Mhm.
Uh,
I'm still confused why. I think broadcasting happened or something of those because I had this tensor of rank one tensor of 784, and it did all the calculations it was supposed to do. Y is equal to mx. The matrix multiplication happened fine. Matrix multiplication would require a rank 2 tensor, and it worked fine. So I think
yeah.
there's a
Yeah.
bit of a catch that happened there. It did an auto calculation, but it did not do this. Requires grad is not something that happened. So yeah, I would like to like this is a huge one. Like it's better that I did it here. Otherwise, if it, I'd like you to understand what the problem was. Here we do a init param with a scalar one. We don't supply the rank tensor like a rank two tensor. It creates a rank one
Mm.
tensor in bias.
It's a scalar, right? So it will
Yeah.
basically multiply with everything. So basically, broadcasting is happening there. I'm not
Okay.
sure how if
Yeah.
you take a 784 rows. Yeah.
Right. I mean, it's like I still haven't got an intuition of like what was the problem was because it did a matrix multiplication, right? Which means it would have somehow unrolled it into a 784 by 1 tensor. But yeah, some things are, I think we have to figure it out from the source code itself. Okay. So then we do basically matrix multiplication where we define this linear model here, right? Which basically says what is the what is the input that we have given. It takes the input and it brings the weights and output from the global function scope, and it does a matrix multiplication, and so that is what its prediction is. So this is our prediction function, model function, and it provides us a prediction, right? Are we clear on this?
Yep.
Yeah.
And yeah, and this is basically we want to see a percentage of what's the like our prediction, like if it is greater than 0.0. So we did a prediction here, right? 20 point, these are the predictions that we have. So we see that what percentage of prediction is more than 0 and what prediction of ours is less than 0, right? And we see that it's approximately 50%. We see that it's approximately 50% is like it's a randomly we assigned and we randomly calculated, so 50% seems reasonable, right? And then what we do here was basically we change the weights of 1 and we retrained it, so we multiplied it by 1.0001 and we retrained it, and there should be a difference in the model prediction, right? But it still gives us is approximately 50% is what we see as the accuracy. And the reason for that is because our function is a discrete, like our difference is a discrete function, right? So when we do this, x into v and this, basically we are calculating, I'm sorry, it's not discrete, but it's in a different range. So that's why we do a sigmoid function calculation here. I'm sorry. Somewhere down the line, I think we did a sigmoid function calculation here. Yeah. So sorry, I blacked out for a few seconds. Okay, so what we saw here was we did a prediction here, and we see that the new items that we have, it is still giving us a prediction of approximately the accuracy of approximately 50%. So nothing much has changed, although we changed our weights by much. The reasoning it says is that, well, our data points are 3s and 7s, right? It's like, is it a 3 or is it a 7? So if we change by a little bit, right, when we change our x by a little bit, our y change doesn't matter that much, because we ultimately calculate whether it's a 3 or whether it's a 7, and it has to be like within a group for that to happen. So a small change doesn't matter much in this scenario, which basically doesn't create our prediction. Our prediction doesn't change much at all for a small change in the weight, because our
Yeah. Basically, none of our predictions changed the class from 3 to 7 or 7 to 3.
Yeah,
So,
because like I was like group, okay, 3, say if it is greater than 0.5 or greater than 0, so it's a huge number, like 0 to 1000, and the weights are independent, right? We are living in the same range of 784, right? We have to this 784 we have to, so it's a huge number. And then we see that, okay, we change our parameters a little bit, and what is the difference that we see? We see that it doesn't change at that much actually. So that is because our groups that we have, it's a bit varied, and that's why a small change in x doesn't do a small change in y, which is not something that gradients works well with. So the concept of gradients is that a small change in x also we should be able to use it to a small change in y, which should be used as a good predictor as well, because at the end of the learning rate is all about taking small steps to go to your destination. Yeah. Is there anything that anybody would like to add over here?
No.
Okay, so that's why what we do is basically we introduce a sigmoid. I'll cover this a bit later. We do a sigmoid function which takes a range of 0 to 1. So this is 0 and this is 1 here. The output is 1 here. And so our output is always within 0 to 1 for whatever range of x that we give, right? So that way we have our output limited to this 0 to 1. And what we can then do is we can say that we can define our loss function as that if my output is 1. So for example, if we can define, here we had defined actually, here we have defined here we are defined, we see tensor 1. So 1 is all output is valid 3 tens. So 1 is basically the output is the valid y contains 1 for the 3s and zeros for the 7s. Okay, so we are mapping it in such a way that 1s are 3s and zeros are 7s, because we have to calculate only between 2. We say that 1s are, so the output is 1, it means it's a 3. The output is 7, it means it's a 1. So the output is 0, it means it's a 7. Yeah.
Yep.
Hello.
Right. Hello.
Yeah. Yeah.
Yeah.
So I think I moved over a bit too much. So basically, our output is like our y is constructed in such a way that 1 is your valid 3s. So if the output is 1, it means it's a 3, or it's a closer to 1, it means a 3. and if it's our output is like, if it's a 0 it's 7, and it's a 1 it's a 3. So our predictions would be such that if it's nearer to 1, right, it's a 3, and if it's nearer to 0 it's a 7. So that's why we use the sigmoid function for this, so that we can map ultimately to what we want. So if it's 1, then tell me, so if the target is 1, then what is the distance between the target and the prediction? And if it's if it's a 0, then what is the prediction? So for example, suppose the prediction came out to be 0.7, right? So it says 0, and we are calculating against a 3. So 3 is a 1, right? So if the target is 1, we'll calculate the 1 minus prediction, which will give me 0.3. And if the target is a 0, it will say that it's a 0.3. So we are saying basically how close are we to the actual output of ours.
Right.
Our prediction, how close it is to our output. And that is what Sigmoid does here. With Sigmoid, we are whatever output we are getting, it's in the, so our matrix multiplication, whatever output we are getting, we are mapping it to this, right? Guys, give me a minute. Hello.
Yep.
Yeah.
Yeah.
Yeah. Yeah. Do you have any questions? Like, do you have any points of discussion? Yeah.
Not me. I mean, I've read about sigmoids and all of this stuff like 100 times in every time. Can you not hear me? Hello?
Hello.
Can you hear me? No?
Oh, sure.
Hello?
You are breaking up for me. I'm not sure. Like, it's the connection, my problem, or
Haswant, were you able to hear me back then?
Yeah, I can hear you both.
All right.
I think it's a problem. Okay, go ahead. Sorry, Usha.
Yeah, I was saying I've studied this part about sigmoids and why we use sigmoid and the loss function, and every time I read it, I'm like I feel lost about it, like getting confused about it. So I'll probably have to go back and read it one more time before
Okay. Um, shall we discuss about it?
No, I think we're good. I mean, I just need to revise it one more time.
Okay.
Yeah,
Guys, I'll just
see.
reconnect it a minute. I'll just reconnect it a minute. Yeah.
Yeah.
So SGD and mini batches is still left, right?
Yeah.
So are we going by chapters and not the lectures?
We're going by the lectures. I haven't reached this point in the lecture yet. Was this a part in lecture 4?
Yes, yes. It's the first half of the lecture 4.
Okay. Maybe we can do the questionnaire from, video 3, the first part of questionnaires, and skip this for next session.
Yeah, we can do that.
Let's wait for him to get back in. Are you with us, Sham?
Hey,
Hello?
Ocean. Yeah, hi. Can you hear me now?
Yeah, we can hear you now.
Yeah.
All right, this admit thing wasn't there until last time, so I didn't really get notified that you were requesting admission to the group.
I had to jump out of. Okay. Okay, so we went through that and we were talking about the sigmoid function. So sigmoid function basically takes an input and it outputs it to a range of 0 to 1. That's all it does. So any function you have, you can do it to 0 to 1. This is basically what we did a bit with normalized functions, right? It's a way of moving it to between 0 point and instead of a linear one, it is much more like until you hit the 0.5, it's a slow growth and um, it's a different kind of curve there. So it starts gradually at first, then increases a bit. The rate of increase is much more. The gradient is much more, and then it again tapers down. So basically, it means that you have a low range of mediums. Like you'll most likely you are anyway other than near 0.5. You will be classified into one or the other. That's what the sigmoid function is basically. You'll be easily classified. So if you are like 0.5 less than 0.5, you are like with this function. Yeah, 0.5. There are actually much more steeper functions than sigmoid also, or you can sigmoid also. You can by adjusting the parameters, you can make it steeper so that it will learn more gradually, and then there's a steep increase, and then it will.
Yeah, but there is a disadvantage to something like that because you wouldn't be able to differentiate between something that is too much on the right of 0. So something that is at 4 is not very different from something that is, let's say, at 20, right?
Absolutely.
Based on sigmoid.
Yep.
So you're not able to compare these two different predictions. So that I think is kind of like a disadvantage or something.
But in case of classification where you have to classify, like it's a black or a white, right? So at that point of time, I'm not saying this best thing about the stuff, but like you can classify it easily.
Yeah, but if you wanted to, get a percentage confidence, something like that, then you would preferably want to have something that lets you differentiate between the two predictions.
Yeah, so basically what sigmoid does is it just calculates the probabilities, right?
Yeah.
Yeah.
Okay.
Yeah.
So if you convert those outputs into 0 to 1, you're basically saying that this is the probability that it is a 3, or this is the probability that it is a 7. So sigmoid is basically used when you're trying for a classification problem.
Right. Okay, so and basically this is what now we have our MNIST loss function, which basically if it's a target is your 1, then it will subtract, it will give a distance of how distant your out prediction is from your 1, and if it's a 0, it will tell you how distant is your prediction from the actual 0 with the help of the sigma function. And then we talk about something called as mini batches. So mini batches are a way of utilizing your GPU to the max. Now, this utilization you have to figure out depending upon what your GPU is, what it is the maximum it can take. For example, here we have a batch size of 256, right? But like depending upon your depending on the GPU that you have. Yeah.
Can we take this part in the next session and do the questionnaire until this point right now?
Yeah. Okay.
If that's okay with you.
Yeah, that's okay.
Covered quite a bit today.
Yeah, I think I've been a bit slow today.
No, we actually have covered a lot.
Yeah, a lot.
Yeah, I mean the lecture 3 video is, he went through pretty much, a lot of stuff back there. Even he stopped in between just to let us, grasp all of it and then cover the rest of it in the next video. So yeah,
let's go to the questionnaire. We'll take it again in batches of 3.
Right.
So one can take the first, Ocean will take the second, I can take the third.
Yeah, sounds good.
Yeah.
Yeah. Who's taking the first one?
I will take.
Yeah.
How is a grayscale image represented on a computer? Okay. So basically it will have only one channel between 0 to 255 values, and the color image will have 3 channels RGB with a range of again 0 to 255. So that's basically how images are stored in a computer.
Right.
Oh,
Next
yeah.
one. So
The next
how
one
the
is
files,
yeah, go ahead, Oscar.
how the files and folders in this sample data structure. So we have a training and validation data folder, and both of them have a folder corresponding to the numbers, each one of the 10 numbers, 0 to 9, and they have the corresponding images. And this is done in this way so that, I'm not sure if there's a particular reason why this is organized in this way, but when you are creating your data block and data loaders, you can specify that the parent folder name is the class that contains that the images represent. So it can automatically label them based on the parent folder name.
And I also think that it has already done the job of separating that training data and validator, so that even if you write a program not by using Fast.ai but using plain mathematics and stuff like that, you don't have to go to this, do the step of changing your training and the validation, separating the training and the validation step.
Right.
Okay,
That makes sense.
take the third. Explain how pixel similarity approaches to classifying digit works. So the pixel similarity, what it does is basically it takes a mean of all the images that are there in a set, and it calculates the pixel difference, the distance between each pixel from the mean and random and the sample image. It takes the mean between them. It takes the difference between them, and it takes
at the end of the day, it takes a mean of the distance between all the pixels. So absolute mean of the absolute value of the distance to get us a absolute mean from the pixel. There is a lot of options. I think that's what pixel similarity. So basically, it says how similar is any sample pixel to the mean pixel average. That.
Yeah.
Hashan. So Hashan, we are doing it in batches of 3. So you are taking the first, 4th, 7th, and then Ocean will be taking the 2nd, 5th, 8th, and I'll be taking the 3rd, 6th, 9th.
Okay, got it. Okay, so the 4th one is what is a list comprehension? So list comprehension is basically, I would say, a technique in Python to create lists using for loops inside the list. So that's basically what a list comprehension is. And create one that selects odd numbers from a list and doubles them. So basically you would have to also add if statement to see whether the given number is an odd number or not. So in a list comprehension, you can add if statements and for loops both.
Right.
So basically it reduces the number of lines that you can use.
Yeah. It takes almost the same time, right? I mean,
yes,
computation-wise,
computationally it is same. It just so that you can write it in a one-liner.
Right.
Yeah.
And I somehow intuitively think that because it means that you don't depend upon a do, you can do it parallelly as well. Because there is no loop involved, so you can separate out the range into different. I mean, maybe the processor might be able to do that. Like if there is 100, then it will divide into 3 patches, and it will calculate the 3 separately, and it will collate them together. But maybe I think parallel also going to turn on.
I'm not sure whether how that it works because in a list comprehension you would definitely need a for loop. It's optional to have if and else statements, but you would definitely need a for loop. So for loop will be cannot be done in parallel, right? So it has to be step by step. So I think the computation is we can do.
If the output of within a for loop, like if they don't modify the loop, the contents of the original array or the
it can be done in that.
I think you can do it parallelly, right? If they are pure functions or like.
Yeah, if given provided the condition that the same value is not getting updated throughout, like a counter or something that gets updated or another value that's getting changed.
The for loop has that flexibility. You can decrease the counter or you can increase the counter, but this is you cannot do it, right? You cannot decrease or increase individual counters. So you have the flexibility where like the underlying OS can take like we have a size of 10, 20, 30 arrays. You have a list of 30 sizes 30. Then you will divide it into 3 batches and you will calculate 3 and then you can collate it.
Right.
I mean, it can be done. I'm not saying it is done. I'm saying I think it can be done.
Okay.
What is a rank 3 tensor? So rank 3 is a 3-dimensional. Rank 3 tensor is similar to a rank 3 array where there are 3 dimensions. One good thing about it can probably do processing on a GPU. So it would, do matrix multiplications and operations much faster and should be able to do calculate gradient and so on as well.
I think rank 2 tensors can also be processed parallelly, right?
Yeah, all kinds of tensors can do. So I was differentiating between a tensor and a number because it is similar to an array.
What's the difference between tensor rank and shape? Tensor rank is basically the number of elements in the not number of elements, the size number of sizes that you have. Like shape basically sees what are the dimensions. Like, okay, it has these many elements and these, and three. It's a tuple of 3, 4, whatever shape. It's a tuple, right? And rank is basically the number of elements in the tuple. How do you get the rank in the shape? Length of tensor. So,
Yeah, length and also and dim.
yeah, and yeah, shape tensor and demo.
Yep. Okay, so what are RMSC and L1? So RMSC's root mean squared error. So what we do here is we will take our predictions and we will see we'll take the difference from the original predictions and take a mean of this and take a square root. So that is basically what RMS is, and L1 norm is basically a absolute value mean absolute value between our predictions and the actual predictions.
Right. Okay, let's take the next one. How can you apply a calculation on thousands of numbers at once, many thousands of times faster than a Python loop? Through broadcasting? And to avoid for loops, you can also do your matrix operations, so vectorizing the stuff. That speeds it up, and then broadcasting also further speeds it up, any kind of operations.
Yeah. I think the matrix is one step. Like you can, rather than looping through the elements of a matrix one by one, you can just do a matrix addition or matrix multiplication.
Right.
It all at once in a GPU capable device. Sorry, create a 3x3 tensor or double it. Select the bottom with phone numbers, tensor of 1 to 9 into 2, and then index it from bottom right 4 numbers. -4 to -1. Minus
4.
Minus
4, right?
-4 to -1. But -1 would not -4 colon and like there is nothing, right? If I give -1, then it will not include -1.
Yeah, -4 colon -1, I guess.
-4 colon, that's all. If you
colon,
give -1, it
will
will exclude the
that one.
So what is broadcasting? Broadcasting, how can I explain this? So broadcasting is a way in which even if your tensors are of not of same size, we can still do matrix additions. So it's basically like we can add a scalar to each and every row if you have a 3x3 matrix, and if you do a +1, it will basically add +1 to each of the element in that 3x3 matrix. So that is how basically broadcasting works. Not sure how to explain it in words.
Yeah, it's okay. I think we understand. We have already discussed it. So it lets you expand an existing matrix to match the dimensions of another matrix, a larger matrix.
Yeah.
Are metrics generally calculated using the range set or the validation set one? Generally calculated using the validation set, because that is the unseen data set that the model is tested upon. Training set, you might end up overfitting on the training set. So, you test it on something that the model is not familiar with.
What is SGD? Stochastic gradient descent. We basically put in different samples, random samples. You can get a random sample and you do it in batches. So that's what you do, the gradient descent on a random sample. SGD.
So why does SGD use mini batches? I'm not sure statistically how it works, but one benefit is we can do it in parallel if you have many batches. And another thing is you will basically be going through towards your local minimum faster, because if you take, suppose you have the whole data and you are taking mean of the loss, so it will basically reduce your loss so that you will be going in a small steps. But if you use a mini batch, your loss will be more, and then you will be going in a step in with respect to the whole batch, you will take larger steps. So those are the two main benefits of using mini batches.
Why would it take larger steps
Yeah.
for the whole batch?
So in a mini batch, you will have less number of samples, right?
Yeah.
So compared to the whole data set, your loss will be a little more.
Okay.
Why?
Why?
Even
Because
if the loss is more, the amount of change is dependent upon the learning rate and the gradient. So it is not really dependent upon the loss, right? The value of the loss per se.
Okay. Not sure how to explain this.
Computationally, it is more effective because instead of calculating the gradient on the entire data set of for every iteration, you are calculating it on much smaller data set. Hold on a second.
Yeah, I have read about it somewhere, but I will let you guys know if I have found some concrete evidence on how to explain this. Okay.
I think like what it does is basically it does parallel executions. Like instead of doing it at one data point or like one input, I think what mini batches is, it allows us to do it on multiple input points. Like for example, we had 256 input points at once, based upon what the GPU capacity you have, 64 input points or 256 input points. I think that's what mini batches allow you.
Yeah.
I mean, I think it would be a bit faster. Like instead of you doing one at a time, it will be faster, but it's a larger scale. I mean, our learn like the number of epochs that we have to do might decrease, or it will take lesser time. They said that it will be like our calculations can be done on
Yeah, actually, yes, we do it. Yeah, even if we do not do it parallel, if you take mini batches, we'll be doing our weights updation faster. Yeah, so it's basically related to time and not the loss.
What are the 7 steps in SGD for machine learning? All right, what were they? So you initialize your parameters, and then you define a function for loss. After that,
predict.
Sorry,
You predict first.
come again.
Prediction.
So
you predict the output first, then you use the model.
Okay. पापा वो फोन कर रहा है, बात करो ना उसको. Sorry. So yeah, you make the predictions, then you define a loss function, and then you calculate the gradient corresponding to that loss function. Is it?
Yeah.
And you optimize the, you move the parameters opposite to the direction of the gradient by a certain amount, depending upon the learning rate. And then you can make the predictions again using those parameters and repeat the steps.
Yeah.
Right?
Yeah.
How do
Guys,
we initialize?
I'm gonna be back in like 2 minutes. There is someone at the door. All right, you guys carry on until then.
Sure.
Yeah.
How do we initialize the weights in the model? Randomly? With a it's random, right? Maybe the only thing that matters is the standard deviation. I
Yes.
still fail to see how standard deviation
Makes
plays
a
a role.
difference.
Yeah.
Yeah, even I was wondering that while watching the lecture.
I think that definitely there will be something to it, but I still fail to see like how standard deviation.
So what is loss? So loss is basically checking how well our model is performing. So if your loss is low, then it's then our model is predicting well. Or else and it is also useful when we are trying to update our weights. So it's basically what a loss is.
Okay. Why can't we use a high learning rate? We don't want to learn too fast, otherwise the steps will, if the steps are too big, maybe it will overshoot. It will never reach the local minimum and it will go towards the maximum. It may go towards the maximum.
Yeah.
Yeah, sorry. Yeah, sorry.
Okay, the next one is, I think, what is gradient? So gradient is basically a derivative of your loss function. So it basically tells you how you should move forward when you're trying to locate your local minima. So you will basically move opposite to what your gradient is. So if your gradient is negative, then you should
Positives.
yeah.
So gradient is like the slope of the function, right?
Yes.
You need to know how to calculate.
Slope is nothing but a derivative of your loss
Yeah.
function.
It's the derivative of the model, right? It's not the derivative of the loss. I mean, we here use it, but I think it's a derivative of the model function.
Yeah, sorry. Not the loss function. No, I think it's loss function, right?
The loss function is basically a calculator, right? Loss function will like what? So our loss function was the MNIST loss. It basically was like.
Okay, I got it. Loss function is dependent on our model function. Yeah, so we are trying.
Loss function is dependent upon our predictions and the actual. So we try to calculate difference. In this case, a root mean square error or an absolute error. That has
Yes.
nothing to do with the model, right? It is basically like how far we are from the actual output.
Yeah, it's the derivative of the function that we are trying to predict. Yeah.
Now, interestingly, what is the derivation of a matrix? So we are doing a matrix multiplication, right? Can we calculate the derivative of matrix?
I think there is this Jakartian that we use.
Which question are we on?
we are on like what is basically
Gradient.
gradient. What is a gradient?
Okay.
This function, what is a gradient? And then Sean made an interesting point. Like gradient is basically a derivative of a function. In case of the model, in this case of the model, which is a matrix multiplication. What
Cannot hear you, Sham.
can you hear me now?
Yeah.
No, like we were discussing about what is a gradient, and
Right.
so gradient is basically a derivative of a function, right?
Right.
And in this case, it's a model function that we do
Loss
the
function.
differentiation. Loss function?
It's the loss function, right? So the gradient that we calculate is for the loss function. We are trying to optimize the loss function.
But we calculate the gradient on the loss function or the
Yes, of the
model
loss
function.
function. We are trying to minimize the loss.
Okay. So it's nothing to do with the model function.
What
But
is the
loss
model?
function, in this case, it was matrix multiplication.
So the loss function is a continuous function that we try to optimize using gradient descent. So when we try to optimize, that means we try to minimize in this case. So the gradient is the slope at different points in the loss function.
Okay, I thought basically it was for the model function. Because we calculate y equals to
the matrix multiplication.
Actually, when you do loss dot backward, it is basically doing derivatives with respect to your actual predictions and your predictions, right? So loss function is a function it's a function of your model function as well as your predictions, right? So it's basically taking a derivative of, so it's like a chain rule. It will also take a derivative of your model function too. In here, it's matrix multiplication.
I mean, a model function would always be a matrix multiplication, I guess. Always it's like ax plus something, or depending upon the activation functions that you use, right? So it would, but loss function would be a combination of your actual values and the model function. And the gradient that you do is of the loss functions to minimize the loss or the cost of the model.
But Oshan, so here's that I'm confused. So we took here an example of loss function, in this case, or mean squared error. But if we had taken absolute mean, which is basically a function of x, it's not like, in this case, it was x square or something like that. If it is a function of x, then that means that gradient is always a constant, right?
Yes.
Yes, the gradient would always, no, in this case, the parameter would change, right? For different parameters, you would get different. So so the parameter would be the slope of x in this case. If it's, let's say, hold on a second, let me just. I'm not really sure how it applies to an absolute function. Norm.
I think we can all, let's put this question in the forum so that we'll remember to read about it. Yeah.
Yeah.
Sure.
let's do this thing. Like if we come across something that we are not sure about, we can, like, we are stuck on something, we'll post in the forum so that we don't forget it. Maybe in the next lesson that we have, next group, we answer it through. And let's go to the next. Like, are we still talking about this?
Right. Indeed. Sia has one. I think he's leaving, so
Okay.
so just us. Which ones do we want to discuss? Do you need to know how to calculate gradient yourself? No, PyTorch can do it for us.
It's good to know, right? Yeah, I still can't figure out how this is.
Yeah.
Is accuracy is a loss function?
I think we
Because
discussed.
it's a metric. It's a metric. Accuracy is a metric for humans. It's not a function which the computer can use to. I mean, it can use, but it would be very efficient in doing that.
And he points out that loss function should be something that changes always with change in parameters. Accuracy might not change in case the prediction is not changed.
If the change in input is low. Yeah.
What is a Sigmoid function? What is special about its shape? Draw the Sigmoid function. What is special about its shape? It has a high slope near 0, and as it moves away from 0, slope kind of decreases and it helps.
Gradually.
All right, you take the next one. Take the next 3, then I take the next 3.
Okay. Difference between loss function and a metric. I guess loss function computer gets that can do really well with the loss function, whereas matrix is better parameter for human consumption. Yeah.
Yeah.
Function to calculate new ways using the learning rate. I think we have to multiply the linear learning rate with the gradient and update our parameters with it.
Right.
What is the function to calculate? What is the data loader class to? Data loader basically batches a data like in a batch sizes and then puts it up to GPUs for calculation. Yeah.
Yeah. So data block is where you define everything and then you use the data block class to instantiate a data loader class. Then you provide it the path. So it creates validation and training many batches.
I think we did here a data loader. We did here a data loader. We created data loaders here. Data. Yeah, we created data loaders here.
All right. Okay. Yeah, right.
Yeah.
Create a function that if passed 2 arguments. No. Write pseudocode showing the basic steps in each. We already tried that and failed miserably. I cannot hear you, Shah. Create a function that if passed to 2 arguments in ABCD returns this. What's special about the output data structure? Output data structure is a list of tuples, I guess. What is special about it? I don't know.
Each tuple contains an X and a Y. Like a data point from one X and Y.
What does view do in PyTorch? I don't know.
View we don't have to know the size. We just need to tell, okay, I want So we had this, right? We had this huge data set, and then we did, okay, create lens of stuff. So basically, it will, what is the maximum you can calculate? You can do this. That sort of use it. It basically it calculates the maximum size in its own. You don't have to define that.
Maximum size as in?
For example, if we give them 10 arrays and 20 arrays, for example, if you want to create a new array, right, of a particular size, you don't have to give that size. It will calculate on its own from the inputs.
Okay, it would. Okay, all right. The rest of it, I guess, have not been covered yet, right? We have not discussed the rest of it.
Yeah.
So let's take them in the next session.
Yeah.
Yeah. So we'll continue on from mini batch SDD topic where we left off, and then also cover the questionnaires. Did you get a chance to work on the your project that you were talking about classifying your images and then putting them in folders?
Not yet.
Not yet.
I have come across a small problem, but